All right, so the title of this last little section is Energy and the Laws of Thermodynamics. So our goal in this section is going to be to talk about different types of energy, which is not new. We've been doing that for several classes now. But to add in the idea of laws of thermodynamics. Now, a law in science is something that has pretty irrevocable proof that it is true. Unlike a theory where we still think that maybe there's a chance it might be wrong, these things are pretty solid. Since you see thermo as part of the title, this means that we are focusing on heat. So the concept of energy developed in part from observations that were made over a number of years about heat and mechanical devices. So what we're going to talk about in this section is what we know about energy conversions based on evidence that we found by observing mechanical devices. And specifically, we're going to talk about motors. Now, very probably last year, you learned about motors and generators, and you might have had to have known all of the parts of them. That is not our focus in this particular scenario. We're going to look at the big picture and types of energy. So we're not focused in on the details about what the parts of a motor are, but moreover, what's the big picture? What kind of energy are we getting? So we're going to talk about a little bit about what happens inside of a motor. But I'd like to start this by asking a bit of a question. My question over here is a perpetual motion machine possible? And so since I have a picture of one, hopefully your answer is probably, otherwise how did she take a picture of it? P.S. I took that picture at the Smithsonian Museum, which is probably the coolest place I've ever been my whole entire life. It's in Washington, D.C. It's the place that if you watch Bones, she works at the Jeffersonian. They're just pretending that it's the same basic place. They're just not allowed, I think, to copyright the name or something. But this object that we're looking at there is a demonstration of what a perpetual motion machine might be like. Perpetual motion means never ending. So the idea that we're trying to get at is, could I make something that starts moving and never ever stops moving? And so I'm going to point out a couple of things that you already know. The first word that I would like to point out is this one, inertia. That's the idea that if I apply a force to an object and it starts moving, it will keep on moving unless some other force slows it down. So take a look at this perpetual motion machine and notice how it's inside of something. It's not just sitting out in the air. The idea is that perpetual motion would only be possible if there were no other forces slowing the object down. So there needs to be the absence of friction. Now usually that means parts can't be touching each other, and so you'll see there's a bunch of like strings suspending things here. That also usually means there can't even be an atmosphere because there are air particles all around that cause small but considerable amounts of friction. And so unless we are in some sort of vacuum, and I'm going to write that word down, unless we are in a vacuum like what space is, then perpetual motion is not really possible. So is a perpetual motion machine possible? Yeah, if we get rid of every other force. And is that realistically going to happen on our planet? No, it's not. We could fabricate conditions to try to make it happen, but in normal setting, it wouldn't be possible. And so we're going to talk about energy and heat specifically to show why that wouldn't happen. Now, before we talk about motors as our example, does anyone want to ask any questions about inertia, perpetual motion? Yes. Vacuum, right. So what happens? Yeah, the wheel spins. And so in this case, I'm pretty sure what the tag on the side said was, like, it's slowing down by like a microsecond every once in a while. So eventually this particular one will stop because they couldn't make zero friction. That was almost impossible. But it's losing such a small amount of energy to friction that it's going to keep on going for a really, 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 really long time. Does anyone else have anything that they'd like to ask? So we're going to talk about engines and motors. So starting at the top, what is an engine? Well, most of you are fairly familiar with a car and that it has an engine. And engines that we typically think about today are man-made devices that use combustion. Now, combustion, you know what that is. We talked about combustion in the very first unit. So just to remind you, combustion is when you take a hydrocarbon, something that has carbon and hydrogen in it. You add oxygen, and you get CO2 and water vapor. Those are the chemical compounds that are produced. But what we'd actually like to focus on in this section is the fact that you also get a whole bunch of heat. Combustion is a very exothermic reaction. That means that as it happens, we're going to produce a lot of heat. So the idea in an engine is that we're going to have this reaction happen. Now, since we're using combustion, we know that we had chemical potential energy. Anytime a chemical reaction is what's driving a machine or a device to function, there had to be chemical potential energy. So the idea would be that I took this chemical potential energy, this chemical reaction happened, heat is produced, and in doing so, we're going to convert energy from one form to another so that eventually my purpose is attained, motion. Now we're focusing on motion because that's the overarching topic in this unit of physics. Obviously, motion is not the only purpose a device could have, but it's the one that we'll concentrate on. So just so that you can get an idea of how engines have changed, in the beginning, there were steam engines. And so I have a picture of a train down here. Trains would be a good example of something that use steam. The idea would be that we use the thermal energy of the steam to create mechanical energy, the energy of motion. Now I'll just point out here a couple of things about steam engines. First of all, what is thermal energy really? Well, thermal energy is a measure of the vibration of particles. Back in grade 8, Unit A, I think, you learn about the particle theory of matter and how depending on how warm or cold a particle is, it's vibrating at a different speed. And so when we're talking about thermal energy, we're really talking about the vibration, the movement, or realistically the kinetic energy that particles have while they're moving. So what we're saying is we're taking the vibration of these particles and using it to make my device move. And so energy is obviously changing from one form to another. The other thing that I want to mention is my end type of energy. You'll notice I'm saying mechanical here and not simply kinetic. And that's because I'm assuming that when we use engines, we are not always exactly at the surface of the earth. When you're in a car, you go up hills, you go down hills. There's no way that you are perfectly at 0 meters above the surface of the earth the entire time. So we're just going to talk about mechanical energy, which we know is the combination of potential and kinetic energy together. Now, modern engines, like I mentioned at the top, use hydrocarbons like gasoline or diesel or propane, something that's chemical, and eventually we will create that same mechanical energy or motion. So over here on the other side is a little picture of an internal combustion engine. Now, the huge details about all of the things that are happening is not the main idea that we're trying to get at. But what I'd like for you to see is sort of the overview of what's happening. In an internal combustion engine like this one, the idea is that we are producing gases that expand and that contract. So when something is a gas, I can change its volume. Since in the combustion reaction, the CO2 and the H2O and frankly the oxygen are all gases, that means that those things could be compressed or expand. And so the idea is that as this reaction is happening and heat is being produced, heat helps compress and expand gases. Now, specifically, heat does the expansion. And so a gas will expand when there is heat. So the idea is that when we perform combustion, we produce a gas and we produce heat. The heat makes the gas expand, and that's what's pushing on pieces of the motor. You might have heard the word a piston before. It's a piece of a motor. It's something that can move up and down. But the idea is that the way we create motion is by making the gas expand and contract. Now that's great. Heat makes things expand. I need something cool to make the gas contract again. So the idea with the motor is that, yes, we produce heat on purpose, but then we have to get rid of it. If we don't, the motor will not keep going back and forth, expanding and contracting the gases. So to make motors work better, here are some things that we'll mention as improvements. So for engines to work better so that they could have more power and move faster and use less fuel, we needed to understand energy conversions and thermodynamics, this idea of heat. And what we realized was anytime we convert energy, there is some waste heat produced. So even if heat is not what I'm trying to get, that's not the purpose of my energy conversion, there's going to be some that is produced. Now with heat, generally comes expansion, like I mentioned. And this can lead to friction. And actually, friction and heat can work both ways. Heat can cause things to have friction. Friction can cause heat to be produced. So one causes the other or vice versa. So the idea was we have to get rid of some of the heat. If we don't get rid of some of the heat, then my machine or my motor, my engine, is not going to function. So here are some examples. In an engine design, ways of eliminating heat had to be incorporated. Things like a radiator, cooling systems, and lubrication. So I'll mention a radiator first. If you think about what the verb radiating means, it means you're emitting some sort of energy. And that's really what a radiator does. You might have seen a radiator before in a building, especially buildings that are older would tend to have radiators. Radiators used to be a way that you could heat a house or a building. And so you might have seen a place where there's a bunch of pipes that go up and down like that. That's a radiator. A radiator had as its principle, if we put hot water and make it flow through these pipes, the heat from the water will transfer from the water to the air in the room and warm up the room. Vice versa, if the water is cold, it will take some heat from the room and use that to warm up the water. And so a radiator is a way of exchanging heat between the motor or the engine and the environment. So it allows fluids to flow through it, and there's lots of surface area so that lots of heat can escape. Now, cooling systems have gotten a lot more advanced. You generally have some fluids in your car that are doing some sort of chemical thing to help cool things off. You might be aware, let's say in a refrigerator or a freezer, if you look at the back of it, there's little pipes and there's an actual chemical substance in there in most cases that is helping the temperature stay cooler. So cooling systems, usually we are talking about some kind of chemical. Now a cooling system could be something as simple as a fan where it's blowing hot air away from the object, but it could also be chemicals that you're adding. Now lubrication would be something like oil. That's what this picture is of over here. The idea that you need to have ways where parts can slide across each other and not have a bunch of friction, because we know that friction could end up producing heat. Things like those that will help reduce either the production of heat, that will help us get rid of heat, or that will help us reduce friction, which in turn will reduce excess heat, all allowed engines to be bigger, to run longer, and to produce more power. All right, so just before I talk about the sheet that I passed out to you while you were discussing this, I'd just like to recap these other three examples. We know what's going in and what's coming out. In this example, we're talking about solar energy, and it says we're getting chemical energy, so we're inferring that photosynthesis is happening. So the useful energy is the chemical energy. The non-useful energy would be heat in this case. In the third example, it's basically the same as the first one. It's a different scenario, but we have the same conversion. And so we could say here that useful energy would be mechanical, and non-useful energy would be heat. In the last one, though, we really can't say that same thing. We're starting out with electrical energy, In this case, our useful energy is our thermal energy. So what other type of energy might be produced that's not useful here? Heat is usually the answer, but this is a case where something else should be the answer. Someone must have a suggestion for this. What else happens when you turn your stove on? Yes. There you go. Non-useful energy could be the light energy. So think about the opposite of a light bulb. When you turn on a light bulb, it gets hot. You don't want that. But it makes light. That's what you want. When you turn on the element in your stove, it gets hot. That's what you want, but it also glows. You don't need light to make things cook, but that would be the byproduct. So heat is usually the non-useful output, but in some cases, it might not be. Now, I could see an argument here for other types of energy. Did you have a question? Now, in a gas stove, I would say the same thing is true because when I light that gas on fire, I can see it. Right? You can see the flame.